Okay, GLS4OM, welcome back. Unit 4, Lesson 5, Derivative of General Exponential and Log Functions. My daughter has told me that if I want to indeed be a true YouTuber, I must remember to tell you to like and subscribe. And don't forget to click on the bell icon. All right, we are dispensing with Euclid problems of the day. I'm really never going to be a YouTuber, I'm telling you. I'm not doing this again when we're back in the classroom. We're no longer quarantined. I'm done with this. No Euclid problem of the day. We have a comic of the day. I'm a bit worried about Mike's obsession with the difference between sine and cosine. And the dad replies, don't worry, it's just a phase. But All right. If you have taken calculus already, then you are quite well versed in how to take the derivative of an exponential function. If you haven't taken it yet, I'll try to walk you through it a little bit. So back to our first principle definition, we need to do f at x plus h. This is f at x plus h. F at x is e to the x. And again, this will be much easier when I get an iPad. It's supposedly being delivered soon. Minus f at x, so f at x plus h minus f at x, all divided by h, and we take the limit as h goes to 0. We can factor, actually I'm going to write this in case you didn't pick up on that. That's e to the x times e to the h. So e to the x plus h can be written as e to the x times e to the h. That's sort of exponent laws in the backwards direction. Turns out being able to work forward and backwards with exponent laws really important for success in calculus. So I could rewrite this as e to the x times e to the h, and then when I factor in e to the x out, I will get e to the h minus 1. E to the x is not dependent upon the variable of our limit, which is h. So e to the x can be treated like a constant. It comes out in front, and then I'm left with this thing here, which is the limit as h goes to 0 of e to the h minus 1 over h. And however your calculus teacher was going to present that the value of this is equal to 1. And e to the x times 1 is e to the x. So the derivative of e to the x is e to the x. The proof that I like to use to show that this is 1 is to do this. We now have this limit in terms of the variable h. It's kind of tough to see what is that actually equal to. So I'm going to create a new limit. I'm going to allow, let me get a different color here. I'm going to allow the numerator to be u. So I've replaced the numerator with u right here. Now, if the numerator is u, then u plus 1 would be equal to e to the h. And then if I bring that over, I get the natural log of u plus 1 should be h. And that came down here. So we replaced the denominator with h. And now I'm going to send h to 0. So if I send h to 0, I'll get e to the 0 here. So I get e to the 0 minus 1, which is also 0. So if h goes to 0, then u goes to 0. So I've changed the limit. This is an identical limit in that they will have the same answer. So the limit is u goes to 0 of u over the natural log of u plus 1. I'm now going to take this u here, and I'm going to write it in the denominator. But when I write it in the denominator, I'm going to have to flip it and write it as 1 over u. So instead of writing u over this thing, I can write 1 over, and I am going to note off to the side for you, 1 over u is simply u. So I can bring that down here. Now the reason we wanted to bring it down there is a law of logarithms that allows the multiplier out in front to become an exponent. So notice how we moved it in to become an exponent now. And then we're going to take a look. This log is not base u. Since the log is not base u, then that limit piece can be applied to the numerator, and it can be applied to this in here. So I know the limit as u goes to 0 of 1 is simply going to be 1. The natural log can be there, and I've got the limit as u goes to 0 of u plus 1 to the 1 over u, and that's a well-known limit in calculus. That's known to be e. So this is 1 over the natural log of e, which is 1. All right, moving on to the next slide. The derivative of b to the x is actually b to the x times ln of b. Now, a couple of ways to look at it. All right, let's use the same method first that we did on the previous slide. So this is f at x plus h. This is f at x, all divided by h. We're looking at the limit as h goes to 0 of that. Again, that's our first principle definition of derivative. Again, this could be written as b to the x times b to the h. I can factor a b to the x out, and that would leave me with b to the h minus 1 in the numerator. And because b to the x is not dependent upon the limit variable, which is h, it can come out in front and be treated as a constant. And then what I have is the exponential function back, and then this stretch or compression factor. That's how I like to refer to it. What is this constant? It turns out that constant, the limit as h goes to 0 of b to the h minus 1 over h, is actually just the natural log of b. So we have the derivative of any exponential function is itself times a stretch or compression factor. Now, walking through the proof again like we did on the previous slide, this time I'm going to replace the numerator with a variable u. When I isolate this expression, I'll get u plus 1, and then I get h is the natural log, or not natural log, log base b. So let me just write that here. B to the h is u plus 1. And then if I'm going to undo this, I'm going to have to, that's a u. I'm going to have to do log base b. So log base b of u plus 1 will replace the h, so the denominator became that. And then we're going to have to take a look again. As h goes to 0, I'm going to get b to the 0 minus 1. That's going to head to 0 as well. So I can rewrite that limit as the limit as u goes to 0 of u over log base b of u plus 1. The u can be brought down to the denominator if you write it as its reciprocal. Then it can become an exponent in here. And the same rules as we did on the previous slide. The limit as u goes to 0 of 1 is 1. And log base b is independent of u, so it can come outside the limit, and then we have this sitting here. And of course that is just e. So this is going to become 1 over log base b of e. And then I'm going to use a change of base formula. So log base b of e can be written as 1 over, I'm going to choose to use the base natural log. It can be written as the natural log of e over the natural log of b. And the natural log of e is, of course, 1. So this is 1 over ln of b, which, of course, just becomes ln of b. That's the same proof as on the previous slide. This one is a different kind of proof. So b to the x could be written as e to the natural log of b to the x. And maybe I'm just going to write that over here. A to the log base a of x is x. That's a property that you learned in advanced functions. So this simply is b to the x. Now why would we do that? Because I can take the derivative of this. The derivative of e to the x. I'm going to use the chain rule here. The derivative of this e to the x is itself times the derivative of the numerator, or not the numerator, times the derivative of the exponent. So I now have e to the x ln b times d by dx of x ln b. And of course the derivative, remember this is a constant, so the derivative of x is 1, I get 1 times ln b. So I'm just going to get e to the ln b times x times ln b. But e to the ln b of x is b to the x. So I get b to the x ln b. So those are two ways to look at the proofs of those. Let's look at the derivatives. Now this will be new. I don't imagine if you were in calculus that you got far enough to see this. So I now want to take the derivative of natural log of x. I'm telling you over here that it is indeed 1 over x. Those of you who haven't had calculus yet won't have seen this. F at x and g at x are inverse functions, right? So the previous lesson we were looking at this formula. G prime at x is 1 over f prime at g at x, as long as these two are inverses, and these two are definitely inverses. I will note, though, that if f at x is e to the x, then f prime is e to the x. So I can rewrite f prime g at x with f g at x, because f and f prime are the same function. F at g at x, I should say. Now, what is f at g at x? Well, if you take a composition of a function with its inverse, you just get one, not 1, you get x back. So that's x. And so 1 over f at g at x becomes 1 over x. And that's one way that we can derive that. And again, I'm just going to repeat. We're making use of this formula, f prime at g at x. But because this is e to the x, and e to the x is the only function whose derivative is equal to itself, if you took the derivative of e to the x a million times, you'd still be at e to the x. We can, instead of writing f prime, just write f. And now I have a composition of a function with its inverse, and that result will always be x. Another way to do it is to start with y equals ln x, and then write this, bring this over to this side, and write it in exponential form. The reason we would do this is because we know how to take the derivative of an exponential, but I'm going to have to use implicit differentiation here. I'm going to have to say the derivative, I'm going to write that over here, the derivative with respect to x of e to the y is going to be the derivative with respect to y of e to the y times dy by dx. And that's going to give me e to the y times y prime. So that's where this has come from. We've used implicit differentiation. If you're not familiar with that, that will be an upcoming lesson. So maybe just follow this proof instead. If you have seen implicit differentiation, then this can make sense to you. E to the y's derivative is y prime e to the y. I will now isolate some for y prime by writing 1 over e to the y. And of course, e to the y is x. So then we just plug in the x. And now we're going to look at the general derivative of any log function. So the derivative of log base b of x is 1 over ln b times x, or 1 over x ln b. They both say the same thing. Let's take a look at this proof. In this proof, I'm just going to use a change of base formula. Log base b of x could be written as natural log of x over ln of b. Now remember, 1 over ln of b is a constant, so I can view this as 1 over ln of b times ln of x. Now when I take the derivative of this, the derivative would be the constant times the derivative of ln x, which is 1 over x, and now I have my 1 over ln b times x. Another proof would involve just the same thing we did on the previous slide. I'm now going to rewrite this in exponential form. I'm going to get b to the y is equal to x. Applying implicit differentiation, the derivative of b to the y is y prime times b to the y times ln of b. That's the derivative of this with respect to y. That's the derivative of y with respect to x. The derivative of x is 1. And now when I isolate this, I get y prime is equal to 1 divided by b to the y over ln of b. But b to the y was x. So I get 1 over ln b of x. And I don't know if I mentioned that over here, that when we took the derivative is with respect to x on both sides. So when we take the derivative of x with respect to x, I get 1. All right, so now some practice. I showed you the derivations, and now we're going to practice taking some derivatives. Maybe we'll do them one at a time. Take the derivative of this one first. And as we've been practicing, mutual pausing, and then I'll discuss the solution. All right, let's discuss this one. We do have a composition of a composition. So this is really f at g at h. The innermost function is x squared. The function in the middle is sine x, and the outermost is 4 to the x. So in that case, I'm going to refer to that as the grandmother. So I'm going to start by taking the derivative of the grandmother function, and I'm going to leave the composition of the mother and the baby inside, so I'm going to leave that right there. The derivative of any exponential function is itself times its stretch or compression factor, and now I'm going to need to multiply by the derivative of the composition of the mother with the baby. Repeating this, the derivative of sine of x squared, I'm just going to recopy all that, I'm not going to read all that to you again. The derivative of sine of x squared is cos of x squared, and then, whoops, I think I need to fix that. The derivative, I jumped ahead, I actually took the derivative. I want to multiply by the derivative of the baby, right? And the derivative of the baby is 2x, so I need an x here. Whoops. I need to squeeze an x in there. So, go like that, x. All right, so now I have negative 2 ln of x times 4 times cos of x squared times 4 to the sine of x squared. Again, which order do you write these? Multiplication is commutative, so any order in which we write it will be correct. Again, I would suggest you take direction from your prof. All right, moving on to, actually I think I'll clone this now. So we're going to do the next one. Clone. I'm going to clear the ink out. So then I'm going to give you some time to think about this particular one. Again, mutual pausing. All right, continuing. How are we going to take the derivative of this? It is a product, so I've laid out the product rule. D by dx of e to the x times log base 5 of x plus e to the x times the derivative of log base 5 of x. The derivative of e to the x is simply e to the x times log base 5 of x plus e to the x. And the derivative of log base 5 of x is 1 over x ln 5. I'm noting now there is a common factor that we can take out. We can factor out e to the x. And when we do that, we get log base 5 of x plus x over ln 5. And now I change this to blue because sometimes in university, this is correct. That is the correct derivative. But sometimes they'll ask you to show that the derivative is equal to a specific value. So I'm going to show you it's possible to continue in our simplification. We can use the change of base formula to write that as ln x over ln 5 plus 1 over x ln 5. Now a common denominator, I'm going to make the common denominator x ln 5. I will now need to multiply this by x. I'll get x ln x plus 1 all over x ln 5 multiplied by my e to the x in front. And again, I'm just showing this to you because sometimes in university you're told to take it to a specific answer, and I'm going to tell you to take them to a specific place on the performance task. All right, next slide. Notice this is a log of a function. So how do I take the derivative of log base b of f at x? So it's 1 over its argument, which is f at x, but now I'd have to use the chain rule, so I'd have to multiply by f prime, and then don't forget it's 1 over the argument times ln of b. And when we bring this all together, the numerator would become f prime over ln b times f at x, but I don't really tend to memorize that as a formula. I tend to think of taking the derivative of a ln of something, a ln of a function. It should just be 1 over the argument times the log of the base, natural log of the base, and then I multiply by the derivative of the inner function. So how about you try and take the derivative of this one? And again, we'll do mutual pausing. All right, so let me try and explain all of what has happened over here. There's a lot of simplification after the derivative. So the first thing I'm going to do is note the derivative of a natural log is 1 over its argument. So it should be 1 over x plus 1 over x cubed plus 1. Then I need to multiply by the derivative of x plus 1 over x cubed plus 1. I'm going to flip this and write it as x cubed plus 1 over x plus 1. Now the derivative of the numerator is 1 times x cubed plus 1. Minus x plus 1, the derivative of the denominator is 3x squared, all divided by the denominator squared, and notice we can reduce out one of these binomial factors. X cubed plus 1 divides into here, leaving me with an x cubed plus 1 and an x plus 1. Expanding, I get x cubed plus 1 minus 3x cubed minus 3x squared, which gives me minus 2x cubed minus 3x squared plus 1, all divided by x plus 1 times x cubed plus 1. And now we can do some factoring. It turns out that f at -1 is 0. If you plug in a -1 into the numerator, you will get 0. So that means x plus 1 over here divides into it. To find the other factor, I did a synthetic division off to the side. -2, -3, 0, 1. -2 comes down, times -1 is 2. -3 plus 2 is -1, times -1 is +1. 0 plus 1 is 1, times -1 is -1, and then we get our remainder of 0. Which we were expecting to happen if it factors, and then that leaves me with -2x squared minus x plus 1. And now it turns out that this little piece here, we do that in green, that you can actually factor this little piece right here. And I did the work up there. I factored out a negative. I got 2x squared plus x minus 1. And that factors into negative 2x minus 1 times x plus 1. So negative 1, there's the 2x minus 1, there's the x plus 1. And, oh my goodness, let's get another color pen here. X cubed plus 1 can be factored as a sum of cubes. So it would factor into x plus 1 times x squared minus 1 plus 1. You can look up the formula for the sum of cubes. And now those x plus 1s cancel out. Distributing that negative through, I get 1 minus 2x all over x squared minus 1 plus x. And again, I mean, technically on this step, we do have the correct derivative. On any of these steps, it's the correct derivative. The question is, how far do you have to simplify? You have to take your direction from your university prof. I just showed you what's possible in terms of simplifying. I'm going to clone that now because that took up an awful lot of space. I'm going to clear the ink out. And now we'll do a pause so we both can have some time to work on the next one. All right, so let's work our way through this particular one. This one is really a composition of several functions. So the outermost function is log base 3. Then we have a sine. Then we have a 4 to the x. And lastly, we have a polynomial t squared. So this is a composition of a composition of a composition. I'm not sure if I need to throw another one in there. This is f at g at h at x. So we are combining 4 different functions here. So we will start now by taking the derivative of the outermost function, which is the great-grandmother function. So its derivative would be 1 over the combination of the grandmother, mother, and baby, times the natural log of 3, because the base here was 3. Then I need to take the derivative of the composition involving the grandmother, the mother, and the baby. The derivative of the grandmother function is cos, and I leave the mother and the baby composition inside. Then I multiply by the derivative of the combination or the composition of the mother and the baby function. So again, repeating this component, that was the derivative of the grandmother, leaving the, no, sorry, that's the derivative of the great-grandmother, leaving the grandmother, the mother, and the baby inside. This is the derivative of the grandmother, leaving the mother and the baby inside. This now becomes the derivative of the mother, 4 to the t, leaving the baby inside, 4 to the t squared times ln of 4, and then I need to multiply by the derivative of the baby. And the derivative of the baby is going to be 2t. So now I'm going to have 2 from here, ln of 4 from there, taking the t from there, and then putting back the combination of the mother with the baby. And this is the composition of mother with the baby. This is the composition of the grandmother, mother, and baby. And down here is the piece that was the great-grandmother with the grandmother and the mother. No, sorry, that was the grandmother, the mother, and the baby. Yes, because the great-grandmother was log base 3. All right, so having worked through all of that, even though I did confuse myself a bit with my grandmothers, great-grandmothers, etc., but that is the correct derivative. All right, next slide. So we have talked about what the hyperbolic functions were. I think we did that in Unit 2. The hyperbolic definition of sine involves using e to the x. So it's e to the x minus e to the negative x, all divided by 2. And if we're going to take the derivative of this, take the derivative of the numerator, the derivative of e to the x is e to the x minus the derivative of e to the negative x is itself, but now because I'm applying the chain rule, I'll have to multiply by the derivative of that exponent. And the derivative of that exponent is negative 1. And I now have e to the x, negative 1 times negative 1 is positive 1. So I have e to the x plus e to the negative x all divided by 2. And that is hyperbolic cosine. So I'm going to get you to derive this one. Show that the derivative of hyperbolic cosine is equal to hyperbolic sine. And again, we'll do our mutual pause. All right, now we're back to continue talking about it. I think this is probably one of the easiest derivatives we've looked at in the past couple of days. D by dx of hyperbolic cos, and hyperbolic cos is e to the x plus e to the negative x all over 2. The derivative of e to the x is e to the x. The derivative of e to the negative x is negative e to the x. And I'm viewing this as a constant 1/2 times the whole thing, so all divided by 2. I'm not going to be using the quotient rule on this. I'm preferring to view this as 1/2 times e to the x plus e to the negative x. And so this would be 1/2 times the derivative of e to the x plus e to the negative x is e to the x minus e to the negative x, which of course is hyperbolic sine. That one was straightforward. All right, the derivatives of, actually coming back over here, notice there is a difference, right? The derivative of sine is cosine, and the derivative of hyperbolic sine is hyperbolic cos. But the derivative of cos is negative sine, and the derivative of hyperbolic cos is positive hyperbolic sine. So there is a difference there. On the next slide, the derivative of hyperbolic tan is hyperbolic secant squared. The derivative of hyperbolic cotan is negative hyperbolic cosecant squared. The derivative of hyperbolic secant of x is negative hyperbolic secant times hyperbolic tan. And notice there's a difference here, like that negative is not there for the circular trig functions. The derivative of sec x is sec x tan x. And now the hyperbolic cosecant, the derivative of that is negative hyperbolic cosecant times hyperbolic cotangent. And let's see where we are now. All right, so we're on to the last slide. All right, we'll split this in two. We'll start with this one. I'll give you some time to take the derivative of this one. Pause, we'll reflect on it, and then we'll go back and do the other one. So pausing so we can take the derivative of this one. Okay, working our way through this one. We're going to start by taking the derivative of the numerator, and I did paste these over here so that we could refer to them. Again, you're likely to be given these on an exam in university. So the derivative of hyperbolic cotan is negative hyperbolic cosecant squared. So negative hyperbolic cosecant squared of t times the denominator minus the numerator. Going to fix that so it does look like hyperbolic cotan, times the derivative of the denominator. The derivative of 1 is 0, and the derivative of hyperbolic tangent is hyperbolic secant squared. And then what I'm going to do is I'm going to split this into two pieces along here. So this divided by this, one of those will cancel out, and I'm left with negative hyperbolic cosecant squared all over 1 plus hyperbolic tan squared minus, I have hyperbolic cotangent squared times 0 plus that is hyperbolic secant squared at t, all divided by 1 plus hyperbolic tan all squared. Oh wait, I think I have to clone now. I'm going to clear the ink out. Put that back. All right, and now I will pause again so we can both work and take the derivative of this one. And this looks like it's a composition of several functions as well. All right, resume our recording, and let's finish up with the last problem for the day. So we really have the outermost function is ln, the inner function is cosh. Actually, sorry, the outer function is 5 to the power 5. It's a power function. The middle function is a natural log, and the innermost function is cosh. So we're going to start by taking the derivative of the outermost function, leaving the other two functions inside. So 5 times the ln of cosh of x all to the power 4 times the derivative of the composition of the inner functions, which is the ln of cosh of h, or ln of cosh of x. The derivative of ln of cosh of x, I'm going to leave that alone, is 1 over cosh of x times the derivative of cosh of x. That gives me 5 ln of cosh of x all to the power 4 divided by the cosh there, and the derivative of cosh is hyperbolic sine. And now hyperbolic sine divided by hyperbolic cos is hyperbolic tangent. So in the end we have 5 times the ln of the hyperbolic cos all to the power 4. So I better bracket that correctly, because the bracket, there's supposed to be a bracket there. It's the ln of the hyperbolic cos all to the power 4 times the hyperbolic tan. And that ends Lesson 5. That one seemed a little bit easier than lesson 4. So thank you for watching. Let me find this piece of paper. What did my daughter say I'm supposed to say? Don't forget to click the bell icon for more notifications. Or oh, so you're notified when I post something new. All right. Take care, guys. See you soon.